Welcome everyone for the Fractal Calculus seminar series. Today we have Professor Kenneth Falconer, who did his undergraduate and PhD degree at the University of Cambridge. Since since then, he has held positions in Cambridge and Bristol, and has been a professor of pure mathematics at University of St Andrews since 1993. In 2017, he was appointed Regus Professor of Mathematics. He has written 5 books and over 130 papers, mainly on aspects of fractal geometry. He is a fellow of the Royal Society of Edinburgh and was awarded the Shepherd's Prize of the London Mathematical Society in 2020 and was awarded a CBE for services to mathematics in 2024. We are very happy to have you, Professor. You may please begin your talk.
Okay, thank you very much for that introduction. Can everyone hear okay?
Yes, we can hear you fine.
Okay, well, it's a pleasure to be participating in your seminar. I think it's partly in Trieste and partly in Paris, but it's lovely to be with you. I'm going to be talking about something that's interested me, and I and various other people at St Andrews in particular have worked on in recent years, namely the notion of intermediate dimensions. So really, I'm going to be interested in fractals in Euclidean space whose different, if you take different definitions of fractal dimension in some sense, you get different answers. So in particular, sets that have different Hausdorff and box counting dimensions. And the idea is that Hausdorff and box counting dimensions can be regarded as particular cases of a spectrum of dimensions, which we call intermediate dimensions, with Hausdorff dimension at one end and box counting dimension at the other end. And then I'm going to talk a bit how potential theoretic methods enable us to study geometrical properties of these various dimensions, such as notions of orthogonal projection or images under certain stochastic processes, such as fractional Brownian motion. So fractals are objects with fine structure of some sort, in that if you zoom in on part of them, you'll see more and more details coming out rather than just flattening out to a line segment or something like that. And fractal dimension in various forms can be used to try and quantify such the amount of irregularity of such sets when viewed at very fine scales. So there are a few pictures of various fractals, and in principle at least you can zoom in on part of them and you'll see generally very small copies of the whole thing in some sense. So let me define two standard types of fractal dimension. The first one, I'm going to be talking about non-empty bounded sets. You can assume the sets that we consider are non-empty and bounded, so that avoids pathological cases. Box counting dimension, you look at covers of your set E by sets of diameter R, or at most R, and you count the smallest number you can get in your covering set. So that's NR of E. And then you look at the exponential behavior of NR as R goes to 0, and the box dimension is defined as the limit of the ratio of that log of that number divided by minus log of R. And roughly speaking, if the box dimension is D, that means that NRE is roughly obeying a power law of the form constant times R to the minus D. Throughout this talk, I'm going to assume that limits like this one exist. To be completely detailed, one needs to look at both upper and lower limits as R tends to 0, but as far as this talk is concerned, we can assume the limits exist, and it doesn't really make much difference. And so the picture illustrates I can take all my covering sets to be balls if I want to, and so I'm just covering my set by as few balls as possible. And there is an equivalent definition of box counting dimension down here. It's the smallest value of S for which I can find a cover of E by sets that are all the same diameter and such that for every positive epsilon I can find such a covering such that the sum of the S powers of the diameters, and they're all those diameters are the same of course, are in the general case, is less than epsilon. So really the box counting dimension is the critical value of S where you can find sums by sets of constant diameter where you can get the convergence of the sum as small as you like or where you can't. And so it's very easy to see that this corresponds to the definition up there because I'm taking all these diameters to be the same. So really this is just the number of covering sets times that diameter to the power S is doesn't go to zero and doesn't blow up roughly. So that's another way of thinking about box counting dimension. Okay, now let's think about Hausdorff dimension. And the standard way of defining Hausdorff dimension is through Hausdorff measures, but we don't need to go down the measure theoretic route. A simpler way of defining Hausdorff dimension is by looking at the putting no restriction on the size of the covering sets and just look at the smallest value you can get for the sum of the S powers of the diameters of the covering sets. I'm using 2 bars to define diameter for a countable cover, and that's HS infinity. So my UI can be any size, and the Hausdorff dimension is given by the smallest value of S such that this infimum can be 0. So again, it's a value of S that that's critical from going from 0 essentially to infinity, or something strictly positive for that. And again, here's a picture, but this time I'm covering my set by small sets of different sizes, and I'm allowed at any size in my countable cover. And then we can write this in an equivalent way. It's the smallest value of S such that for all positive number, I can find a cover with no restriction on the diameters such that the sum of the S powers of the diameter is less than or equal to epsilon. That can be shown to be equivalent to the dimension there. And I'll be coming back to those definitions shortly. So here are some self-similar fractals. A compact set, and we'll just really be talking about compact sets, is self-similar if it can be expressed as a finite union of images itself under a collection of contracting similarity mappings. So these are self-similar sets. So for example, this one is equal to its union under 6 reduced size copies of itself. And similarly for these, you've got 2 different scales operating for the snowflake, and then that's the right-angled Sierpinski triangle. And for self-similar sets, it's always the case that Hausdorff and box dimensions are equal. And in many cases, provided there's not too much overlap in this union, then the dimension is given by solving the equation sigma Ri to the power S equals 1, where Ri is the similarity ratio of the ith mapping, or scaling ratio. And here's a particular example, the right-angled Sierpinski triangle. I've written down the mappings, but it's obvious from the picture. They're the similarity transformations that map the large triangle onto the 3 smaller triangles. And then the Sierpinski triangle satisfies the fact it's made up of the union of its 3 copies under those mappings. And indeed, it's a unique non-empty compact set that satisfies that condition. And you've got 3 mappings scaling at 1/2 for each. So very easily you get the dimension is log 3 over log 2. Okay, and here you can see those are also self-similar sets. The Bangkok curve and the snowflake, it's fairly obvious. Maybe this multi-armed spire is a little bit less obvious, but that is the image that equals itself under the image of two transformations, one which maps the whole thing by a very large contraction onto this little bit, and one which maps on the whole thing onto the rest at a scale slightly less than 1 and rotates slightly. And then just with two transformations, you can get things like that. So those are self-similar sets. I'm also going to be thinking a bit about self-affine sets. And for self-affine sets, the only difference is instead of looking at contracting similarities, we're now looking at contracting affine mappings. So here are a couple of self-affine sets. This one, you map the square onto these various parallelograms in this case. So an affine map, of course, is a linear map plus a transformation. And so you get this identity by the Hutchinson theory and so on defines this chain-like set or this cross-like set. So here, these sets are made up of reduced scale copies, affine copies of the whole thing. And in a certain sense, generically, self-affine sets have equal Hausdorff and box counting dimension, but there are many instances where you don't get the Hausdorff and the box counting dimensions equal. And that some of those are going to interest us in what follows. And a particular class of self-affine set are the Bedford-McMullen carpets, self-affine carpets. Here, our transformations map, well, it's two dimensions, R2 to R2. They're affine transformations which map the entire unit square onto each of these rectangles. There are two rectangles down there without rotation or reflection to begin with. And so that left-hand template, if you like, defines what the mappings at SI are. And by repeatedly substituting that picture in itself, you get the self-affine carpet, which is, I don't know how clear it is because obviously the actual carpet is so fine you can't actually see it. But that might give an impression on the right for a particular example of a Bedford-McMullen carpet defined by that collection of affine mappings. And as we'll see in a moment, typically for Bedford-McMullen carpets, the Hausdorff and box dimensions differ. There are a couple of generalizations of Bedford-McMullen carpets, Gazzuri-Lalli carpets, where you can have different ratios, provided you've got a rigid horizontal vertical structure somehow, and similarly for the Baranski carpets, where you've got a division into by horizontal and vertical lines, and you choose some of the regions defined by those. And again, for such carpets, the box counting and Hausdorff dimensions differ. Here's a rather simple example where you've got different box counting and Hausdorff dimensions. This is simply a countable set, a sequence 1 over n to the p together with 0, which is plotted on this line. It's a countable set, and the Hausdorff dimension of any countable set is 0. So we've got something of Hausdorff dimension 0, but the box dimension is strictly positive. In fact, it's taking the exponent p there, the box dimension of that infinite sequence accumulating at 0 is 1 over p plus 1. And the way to calculate this is, when calculating the box dimension, given a small r, you choose the largest k such that the difference between the k and k plus 1th terms in the sequence is bigger than r, so you go along as far as you can with the gaps being bigger than r. and then you cover your set by intervals of length r for each of the points up to there. And then when you get to the point where the gap equals r, then you just fill the remaining interval from 0 to that relevant value of 1 over k to the p by intervals of length r. And by choosing that cover, you can show that's the minimum. And by counting the number of sets in that cover, you will get dimension 1 over p plus 1. So that's a simpler example where you've got Hausdorff and box counting dimension differing significantly. So let's come back to Hausdorff and box counting dimensions and think a little bit about intermediate dimensions. And you can recall from what I said a bit earlier, there are these equivalent definitions of Hausdorff dimension and box counting dimension by looking at the smallest value of S, such that for all epsilon we can find covers such that the sum of the S powers of the diameters of the covering sets are less than epsilon, and you can do that for all positive epsilon. So for Hausdorff dimension, there's no restriction at all on the size of the covering sets. For box counting dimension, essentially you have to have the diameters of all the covering sets equal. So that's one extreme, no restrictions at all on your covers. Here, a very strong restriction that you have to have them all equal. Well, you don't have to have them all equal. If you take the diameter of a smaller set and put it in something of the same diameter as everything else, it won't change the definition of box counting dimension. So we've got no restriction, a very strong restriction, and what we want to do is to interpolate between those two definitions of a dimension. And so what we do is, for a non-empty bounded set, and for a value of theta between 0 and 1, we define the theta intermediate dimension by the following expression. It's the same as these two expressions here. We want for all epsilon greater than 0, and we want, and what matters is just when the covers are fairly small, so we'll have all delta positive sufficiently small. We can find a cover such that you've got the sum of the S powers of the diameters of the covering sets no more than epsilon, but there is a restriction of the size of the covering sets. The diameters of the covering sets have to be between delta to the 1 over theta and delta. So we are only allowing, for each delta, we're only allowing coverings in the range, a limited range from delta to the 1 over theta up to delta, or you can write it the other way, from delta up to delta to the theta. And notice if you put theta equals 0, that's essentially make that term 0, so there's no restriction on the covering, it's just sufficiently small. Whereas if you put theta equal to 1, then that simply requires that the diameters of all the ui are equal to delta. So by putting theta equals 0, you recover Hausdorff dimension. By putting theta equals 1, you recover box counting dimension. And so that's how we define the theta intermediate dimension. But the main thing to bear in mind is that these intermediate dimensions provide a spectrum of dimensions. At one end, when theta equals 0, you get Hausdorff dimension, and when theta equals 1, you get box counting dimension. I'm just repeating that definition here, just to provide a bit of visualization. So the definition is the same, except for this restriction on the diameters of allowable covering sets. So you've got the Hausdorff dimension here, no restriction at all. Box counting dimension, you might as well have all the covering sets of the same diameter. An intermediate dimension, you're allowed a range of delta to the 1 over theta to delta of the size of sets you're allowed in your covering. So that's a sort of pictorial idea of the difference as theta varies between 0 and 1. And some obvious remarks. I've already said that when theta equals 0, and 1 you get Hausdorff and box dimensions. And it's very easy to see that for other values of theta, you're lying in between the two. As theta increases, you're putting more and more restrictions on the allowable coverings. You're narrowing down the range of diameters that are permissible, and so that means that the theta intermediate dimension is going to increase from one end of the spectrum to the other. And we can make some very simple observations on this. Very roughly speaking, intermediate dimensions when theta is strictly bigger than 0 behave a bit more like box dimensions than Hausdorff dimensions. But provided the dimensions exist, then there's got finite stability. The theta dimension of the union of two sets is the maximum of the two individual dimensions. Provided theta is strictly positive, the theta dimension doesn't change if you replace a set by its closure. And then there's a product rule. The theta dimension of E cross F lies between the sum of the individual theta dimensions, and you get a weaker bound on the upper end between the theta dimension and the box counting dimension of F. And then the intermediate dimensions are by Lipschitz invariant. They behave well under by Lipschitz mappings. If you look at the image of a set under a by Lipschitz map, then the theta dimension doesn't change, which is just an extension of the corresponding result for Hausdorff and box dimensions. So those are some basic properties. Marginally more involved property is that if you've got a given set and you compare the theta dimension for two values of theta, where phi is bigger than theta, then the theta dimension is always less than or equal to the phi dimension. That's the increasing bit, and that's going to be less than or equal to phi over theta, provided we ignore the case when theta equals 0 there, times the theta dimension. And of course, a consequence of that, if I let phi decrease to theta, then that means that we can see that provided that theta is bigger than 0, the intermediate dimension is continuous in theta. And as I've remarked, it's increasing, though it doesn't necessarily have to be strictly increasing. And the proof of that is really just straightforward. If you take a cover UI of the set E with the diameters of the UI lying between delta and delta to the theta and the sum of the S powers of the UI less than epsilon, then we can reduce the range of permissible sizes by, if we look at all the covering sets whose diameters are between delta and delta to the theta over phi, and replace them all by a larger set with diameter delta to the theta over phi, and that will give us a cover by sets U primed I whose diameters are in the range delta to the theta over phi to delta. And then if we just look at what happens to that sum when we've made this replacement of the smaller cases, that sum basically becomes that the sum of the UI primed to the S times phi over theta is less than epsilon. So that means that the dimension doesn't go up by more than a factor phi over theta. So that gives that inequality. So let's come back to this example. And we've already remarked that for the 1 over n to the p sequence, the box counting dimension is 1 over p plus 1, and the Hausdorff dimension is 0. Well, you can do exactly the same sort of calculation where you allow coverings over a range delta to the 1 over theta up to delta. You look at the gaps, and you choose a cutoff point there, and between 0 and the cutoff point, you cover using the largest possible size of intervals. You cover these by intervals of size delta, and then you cover the remaining points by intervals of the smallest allowable length. So these will be of length delta, so coverings by intervals of length delta for the individual points, and near this end you're just covering everything with as larger intervals as you can of length. So it's going to be length delta for those and length delta to 1 over theta for these. Sorry, I was getting them the wrong way round. So, but by taking a cut of these points and using one size interval to the left and the other size interval to the right, it's easy to derive that formula. Okay, so here are some examples. And one thing to note about these examples is sometimes we get a discontinuity at 0, sometimes we don't. So sometimes the limit as the intermediate dimension as theta tends to 0 equals the Hausdorff dimension, and sometimes you don't get that. And we're still looking actually for a nice characterization of the sets where you get a jump point at 0, and you don't, where you do or don't get a jump at 0, and a condition that separates those on the set itself, and that you can get some rather artificial definitions which don't really tell you anything, but we're wondering if there's anything more intrinsic to the set. So taking reciprocals of log n, you've got very slow convergence, and the dimension is going to be 1, except because it's countable, Hausdorff dimension is 0. If you take the 1 over n set and take the union of some self-similar set, say of dimension 1/3, then you get a straight bit and then increasing from there. And by taking E1 union E, where E some set with equal box counting dimension and Aswa dimension, don't worry about that, to be equal a quarter, then you can get a jump at the start and then flat and then increasing. And if you take, for example, the product of the 1 over n set and the 1 over log n set, and look at the intermediate dimensions of that, then you get a jump and then gradually increasing up to the box counting dimension. So those are some basic examples. Here are some slightly more sophisticated examples. We have a nested sequence of ellipses, which can be determined in that way, and a sort of it's not you've got separate curves there, and for the spirals, these are spirals, and so it's a continuous curve, but because of the rate at which the consecutive loops of the curve approach the origin, you get a similar formula for both the spirals and the nested ellipses, and that's the formula there. And in fact, it's turned out that there's something called the unwinding problem for spirals. Given two spirals, what can you say about mappings that are either by Lipschitz or satisfy Holder conditions between your two spirals? And these intermediate dimensions can provide restrictions on the possible Holder exponents and so on that you can have mapping one spiral to another. Let's come back to Bedford-McMullen carpets. That's the one we had before, the 3x4 one, and there are a couple more. That's a 2x3 carpet, so just dividing into 2 columns, 3 rows, and this is a 3x5 column, 3 columns and 5 rows, and they're constructed in exactly the same way by repeatedly substituting blocks inside blocks. And these were first looked at by Tim Bedford and Kurt McMullen in 1984. who both of them independently calculated the Hausdorff and box dimensions of these carpets. And those are the formulae. Don't worry about them too much. They depend on, you look at the row and column structure. So we've got here P columns, Q rows, and NJ is the number of rectangles selected in the jth column, and the dimensions depend on those numbers. But you only get equality of Hausdorff and box counting dimension if every column has exactly the same number of selected rectangles. The box dimension calculation is quite easy. The Hausdorff dimension calculation is a little bit harder, but basically you have to define the appropriate measure on the carpet and look at its local behaviour. So that's the Bedford McMullen carpet. And when John Fraser, Tom Kempton and I started looking at intermediate dimensions, we thought the Bedford McMullen carpets were a good case to try out, because different Hausdorff and box counting dimensions, but the best we could get was lower and upper bounds for the intermediate dimensions, and the lower bound was going away linearly in theta from the Hausdorff dimension, and the upper bound was again near zero, which is relevant near zero, behaves like Hausdorff dimension plus 1 over minus log theta, which means it does approach zero as theta goes, sorry, it does approach the Hausdorff dimension as theta goes to zero, but very, very slowly. But at least those estimates, and we could find reasonable expressions for these constants C1 and C2, which I'm not going to bother you with. But at least that was enough to show that the Bedford McMullen carpets had intermediate dimension that was continuous at zero, and therefore everywhere. So those are the sort of bounds that we got: a very poor upper bound and linear lower bound. And we spent quite a lot of time trying to get better estimates, but it was quite difficult. And we came to the conclusion that actually getting an expression for the theta intermediate dimension of the Bedford McMullen carpet was completely out of reach. And so we were rather amazed when one of our research students and one of our postdocs actually managed to obtain an expression for the intermediate dimensions of the Bedford McMullen carpet. And it's the most extraordinary formula I've ever come across. You let gamma be the ratio of the logs of the number of which way round it, number of rows, number of that's a number of columns, number of rows, so it's that way round. And for each between consecutive powers of gamma, there's a different formula. The dimension equals S, where for each of these ranges you have to look at the solution of this horrible expression here, but it's rather more horrible than it appears. T is a function that depends on the number of columns and rows that you have. Tk is the kth iterate of that function, and L is the Legendre transform. So really that is an extraordinarily complicated formula, and I have no idea how our colleagues managed to get hold of that. But basically there's between consecutive negative powers of gamma, there's a slightly different form because you have one more iteration of this T function, and the intervals just accumulate at zero. And immediately there are various corollaries of this. Firstly, that the theta dimension exists, in other words, the upper and lower versions in a sort of limiting sense are the same. It's continuous on the whole thing and strictly increasing. On each of these intervals, it's real analytic, but at each gamma, negative power of gamma, the derivative is discontinuous. And then near the origin, you've got a constant over log theta squared, which gives the same sort of approach to the origin as we'd actually got before. And in fact, using the definition, you're looking at coverings by sets of intervals of diameters between delta to the 1 over theta and delta, and you need far more than just taking a combination of the smallest possible and the largest possible intervals of lengths of intervals in that range. You're using intervals in the entire range between delta to the 1 over theta and delta, intervals of length across that entire range of permissible lengths. And it's really an extraordinary calculation. Really, it's one of the most impressive pieces of mathematics that I've come across recently, just for the sheer technical manipulation involved. So that's Bedford McMullen carpets. And then another thing one can look at is we've got this condition relating that we saw earlier, relating the intermediate dimension for two values of theta and phi in that, but one can get more exact estimates by comparing covers over one range of deltas and another range of deltas, and you can actually get stronger estimates than just these. And in particular, one can get an inequality here between, if phi is bigger than theta, express quotients of this form. And so that is a necessary condition for the increase of the intermediate dimensions. And it turns out that this essentially gives a complete characterization of the functions one can get as intermediate dimensions when theta ranges from 0 to 1. And again, Banerjee and Alex Rota showed that if h is a function from the unit interval to 0 to n, then there exists a set E with intermediate dimension equal to h of theta, if and only if h is non-decreasing continuous and the upper Dini derivatives, which is defined in that way, are always less than or equal to this expression. So we've now got a complete characterization of the functions one can get as the intermediate dimensions of some set or other. Let me now think a bit about the geometry of intermediate dimensions. Going back a long way, the mass transprojection theorem, which was generalized by Perti-Mattila to higher dimensions, says that if you've got a set in n-dimensional Euclidean space, then the dimension of the orthogonal projections onto an m-dimensional space are, for almost all directions of projection, given by the minimum of the Hausdorff direction of the original set and the dimension of the space on which you're projecting. So proj denotes orthogonal projection onto whatever m-dimensional subspaces you're considering. And one way of thinking of the minimum of the Hausdorff dimension of E and M is you think of that as viewing the set from an m-dimensional viewpoint, looking at the m-dimensional shadow, if you like. And we call that the m-dimensional Hausdorff dimensional profile. And you can just define this quantity for values of m that aren't integers if you want. So I'm not going to say very much about proofs or anything, but going back to Frostman, it's known that the Hausdorff dimension of a set can be expressed as a capacity. Oh, sorry, actually, I'm skipping slightly. Because orthogonal projection is a Lipschitz mapping, it's immediate that the Hausdorff dimension of projections is never any more than the minimum of the Hausdorff dimension of the original set and the dimension of the space onto which you're projecting. But the lower down, which holds almost surely, one can use capacities or energy methods. And as I say, this goes back to Frostman. You define the capacity of a set with respect to the kernel 1 over x absolute or length of x to the power s by the reciprocal of the capacity is the minimum energy over probability measures defined in this way. And then Frostman pointed out that the Hausdorff dimension is the largest value of S, which makes the capacity equal to 0. And alternatively, it's the largest value of S for which the energy can be finite. You can find a measure such that that energy term is finite. And once you've got that, it's very easy to obtain, well, in the two-dimensional case, Marstrand's projection theorem. Simply, you put appropriate measure on the set E, and you look at the projections of that measures onto the lines in direction alpha, and you look at this integral. That is the energy of the projected measure with respect to the kernel 1 over t minus u to the power s, and then you integrate that over alpha going from 0 to pi. And because of the definition of the projected measure, you can replace the projected measure at t by the original measure and replace the t by x dot alpha, where alpha is the direction of the line of projection. And then you get equality, well, to within a constant there. And now if you integrate this 1 over x minus y dot alpha to the power s, you're basically integrating 1 over cos theta to the s, and that converges if s is less than 1. So provided you can find a measure on your set E such that that energy is finite, then this has to be finite for almost all of the projected measures, and that gives you the dimension of the projected sets bigger than S. Okay, so that's Hausdorff dimension. We've already met the box counting dimension as the limit as the log of the least number of sets of diameter at most r divided by minus log r, the limit of that, or you can take disks instead of arbitrary covering sets, it doesn't matter. And one asks whether there's a Marstrand type theorem for box counting dimensions. And back in the 1980s, Marek Jarvenpaar came up with examples where you can actually get a drop of box counting dimension in by choosing your set appropriately. It's not necessarily equal to the minimum of the box dimension of the original set and the dimension of the space onto which you're projecting, but it can be this small, and that's the best possible values. So you can get a dimension drop. I was working with someone called John Howroyd around about the time, and we were able to show that, in fact, nevertheless, we have a Marstrand type theorem such that the dimension of the projections must be constant for almost all alpha. In 1996, we had a very messy argument that established that. But more recently, we've noted that if we look at a potential theoretic method, the difference from working with the Frostman characterization of Hausdorff dimension is that for box counting dimension, you have to use kernels of this form that are 1 for small r and then decay like r over the length of the vector s, vector x to the power s further away. So you've got a kernel which behaves like that. And the reason for using that, at least in the plane, is that if you look at the kernel evaluated at x minus y, which is by definition that, then that's the Lebesgue, gives you the Lebesgue measure of the directions alpha, such that the projection of the vector joining 2 points has length less than or equal to r, and that's crucial in doing the calculations. And then, just as with Hausdorff dimension, you can look at an energy interval, an energy integral with respect to that kernel, and you can look at the minimum energy, and the capacity with respect to that kernel is just the reciprocal of that. Again, you're looking at the infimum over probability measures on your set E. And so it turns out that with n r the least number of sets of diameter r that can cover E, the capacity with respect to this kernel here almost gives you the number NRE, at least within a logarithm. So that means you can actually define the box counting dimension in terms of these capacities, and you get the same answer. Doesn't matter whether you take the box counting number there or the capacities with respect to the kernel 1 r over length of x to the power n, you get the same answer. And that turned out to be key to getting rather nicer proofs of the projection theorems. So for box counting dimensions, you first get the box counting dimension using the capacity with an n there, but to get to projections, you simply look at the capacity with respect to the kernel where you have an m rather than an n, where you're projecting onto m-dimensional space. So you get the dimension of the box dimension of the projections equal this quantity here, which is the limit of the capacities with respect to the kernel, the minimum of 1 and r over length of x to the power m. And we call this the m box dimensional profile, where the capacity is defined by these kernels. So what I'm suggesting is we can think of finding dimensions, Hausdorff and box counting dimension, in terms of capacities, and we get a dimension profile which depends on some exponent of the kernel, and this is similar but with the different kernel for Hausdorff dimension. And again, we think of this quantity here as the box dimension of E when you view it from an m-dimensional perspective, m-dimensional viewpoint. Okay, so coming back to intermediate dimensions, I'm not going to go into any detail at all here, but one can do similar things with these kernels, where to allow for the change in allowable covering, you get this kink in the kernel. You've got these 3 parts, one when r is small, r over length of x to the power s, when between r and r to the power theta, and then this decay when the length of x is bigger than that. And again, we can define the capacities with respect to this kernel, and we can define these quantities, which we think of as a dimension of E, the intermediate theta dimension of E, when viewed from an m-dimensional viewpoint. And basically, they're a unique S such that that is satisfied. Putting m equals n, you get that back. You recover the theta dimension of the original set, and when you have smaller values of m, then you get the dimension, almost sure dimension of the projection, the almost theta dimension of the projection for almost all directions of projection alpha. And it's the same sort of idea, but the details are a bit more complicated for the intermediate dimensions. Okay, so those are results on projections. So I'm going to end by just saying a little bit about another aspect that we've examined of intermediate dimensions, Let's look. We're going to look at fractional Brownian motion. Here's a graph of Brownian motion, which you remember is a stochastic process. It's a Gaussian process that passes through zero independent stationary increments and an increment of length. An increment of length h has mean zero, and the variance is the length of the interval over which you're looking for your increment. So that's essentially the definition of Brownian motion. And once you've got Brownian motion, you can use a stochastic integral, a stochastic fractional integral, to define fractional Brownian motion. So index alpha fractional Brownian motion can be defined. C of alpha is just a constant, which you needn't worry about, a normalization constant. And then we look at the integral with respect to Brownian motion, the stochastic integral of this expression, the positive part of t minus x. So plus simply means if that's negative, you just take zero. If it's positive, or ignore it altogether. If it's positive, then you take that value. And so t minus x to the power alpha minus a half there, and minus x to the alpha minus a half there, again the positive part. The two terms are necessary to ensure that you go through the origin. And when alpha actually equals a half, you recover Brownian motion, in which case you have to take this expression to be the indicator function of naught up to t. So that's one definition of fractional Brownian motion. And let me just list very briefly some properties of fractional Brownian motion. Here's the graphs of realizations of it going from alpha goes from 0.1, 0.3, 0.5. That's the Brownian case, 0.7, 0.9. Fractional Brownian motion is a Gaussian random process through the origin, continuous almost surely. The increments are normally distributed, are Gaussian, mean zero, and variance, the length of the increment to the power twice alpha. So putting alpha equals a half, you recover Brownian motion. And various things can be derived about fractional Brownian motion. For epsilon greater than zero, you've got an almost sure Holder condition on the Brownian motion. The increments, the image increments no more than a constant times the length of the increment to the power alpha minus epsilon. And the graph of fractional Brownian motion, index alpha, is 2 minus alpha almost surely. And then you've got a stochastic self-similarity, the distribution of, if you scale the time by lambda, then that's the same, has the same effect as scaling. If you scale the spatial term by lambda to the alpha, then you get the process with exactly the same distribution. And so one is interested, and this goes back certainly to Vesikovich, Taylor, and various other mathematicians, in the relationship between the dimension of a set E and of its image under these sorts of processes. So that's a question one might ask. And it turns out that for index alpha fractional Brownian motion, if E's, let's say, is compact, almost surely the theta dimension is given by this expression. It's never negative, of course, but in the interesting case, it's 1 over alpha times the dimension of this is the what is it? Sorry, I glossed over this. This is the this expression here, the m theta intermediate dimension profile with respect to the these kernels. And when you've defined that, then taking that alpha dimensional profile of the intermediate dimension, you get this essentially gives you the value of the almost sure value of the image dimension under index alpha fractional Brownian motion. So you've got several things going on here. And for fractional Brownian motion, this was proved a long time ago in the 70s, I think, by Jean-Pierre Cahan for Hausdorff dimension and Yimin Zhao for box dimension a little bit later. And the proofs are actually quite similar to those for projections, and the way you use capacities and see how the capacities change under transformation by the fractional Brownian motion. So that's my SOP to fractional integration, that fractional Brownian motion can be thought of as a fractional integral against Brownian motion. So there's various results on intermediate dimension and the various other things we've managed to prove, but I think that's probably enough for now. So thank you very much for your attention. I hope some of that at least was of interest to you.
Thank you very much for the nice talk. For questions, please raise your hand. I'll call out your name in the order they appear on my screen. I don't see any raised hand, but if you still have a question or a comment, you can unmute your mic. Okay, I see. Professor Yulia Mishra has a question.
Yes, I have the following question. So you calculate the fractional and other dimensions of fractional Brownian motion, but these calculations depend on what is your feeling? These calculations depend on a covariance function, incremental covariance, or on the stochastic representation. I ask because there is a lot of generalizations of fractional Brownian motion with different covariance functions, but not very different. And is it possible to generalize these results to more general classes of processes? What do you think?
Well, basically what we use, coming back to this, if you can still see the slide, we basically we don't go back to the definition of fractional Brownian motion, but we actually use these properties here. Basically the variance condition and independent increments. I mean, those are the key things that we use. As you say, there are several essentially equivalent definitions of fractional Brownian motion, but it's the properties rather than the definitions that we work from, that we've got a Gaussian process, and you've basically got, for calculating the theta intermediate dimensions, then you've got what happens over three scale ranges, the small scale range, then the intermediate scale range, and then the long range term. So it's basically we use the well-known properties of the stochastic processes, and I know that there are other types of stochastic processes where you can do this sort of thing. I can't even remember what they're called, but something I wrote with Yimin Zhao some years back, which we originally started off looking at fractional Brownian motion, but there was a larger class of functions which were sufficiently close to having these properties that we could do such calculations with them.
Thank you very much.
Is it possible to interpret intermediate dimension as a part of multifractal spectrum in multifractal analysis, as partial case of multifractal spectrum?
Well, that's a good question. I mean, thinking of the intermediate dimensions as a spectrum is, spectrum's possibly not a good term there. And we've got a range of numbers that we get. Multifractal analysis, of course, depends on a measure.
Yeah.
And we're studying sets rather than measures here. However, something we're looking at the moment is where we try and do this sort of thing with measures. So, there are natural and not so natural measures that you can put on things like the Bedford-McMullen carpet or even the sequence sets. And we've got some results and are fairly rapidly getting some more, I think, when instead of just thinking about the sets, we define multifractal-like expressions on those sets. So, intermediate dimensions themselves are not, I would say, multifractal concept, but we are extending them, and they can be extended to a theory for measures rather than sets. So, yeah.
Okay. Thank you very much.
Are there more questions? You can unmute your mic.
I have a maybe very naive question. It might be a stupid question because I'm not working in this topic, but if you have applications of fractals, you want to use the theory of fractals somewhere, would these intermediate definitions between Hausdorff and box counting, would they be useful? And how would you know sort of which value of theta to take to make it?
I mean, maybe I'm being a bit naive, but for most of the practical definitions, if you're going to do very much, you're probably using box counting dimension. Hausdorff dimension of a real object is actually rather hard to try and calculate, and given that you normally, for applications, only have a limited range of scales, it's quite difficult. And it would be very nice to come across some examples which would demonstrably had a different Hausdorff-like dimension from box counting-like dimension, at least over a good range of scales. Okay, if you get into theory like maybe theory looking at turbulence from a fractal point of view, it may be possible theoretically to show that for certain aspects of turbulence, it does make sense. In theories where you can actually take the limit as the scale goes to zero, to have different Hausdorff and box counting dimensions. And indeed, since you are actually, in a sense, applications such as turbulence or dynamical systems where you've got more stretching in one direction than other directions, you've got something that's more like self-affine than self-similar. So they might, well, at least in some of the theoretical models, you get something like different Hausdorff and box dimensions, in which case we can look at the intermediate dimensions. Whether intermediate dimensions have any direct applications, well, we haven't thought of any yet.
Okay, thank you.
But if you think of any, then let me know.
Well, I'm a pure mathematician as well, so probably not me. Maybe Pavan, who knows?
Maybe in my view, all theta are important. Different theta, you have an object and you have an intermediate, spectrum, whatever. And for different theta show you different properties of this fractal set.
Yeah.
That's I would say, interpretation.
Yeah, that's the way I think of them, and certainly it tells you more by knowing something about intermediate dimensions, say for relatively small theta. That tells you something about the distribution of the size of covering sets that you're going to need for when you calculate Hausdorff dimension. I mean, it's well known that for certain sets, if you're going to calculate Hausdorff dimensions, then you'll need relatively large covering sets for parts of the set and relatively small covering sets for other parts of the set. And the intermediate dimension will give you some indication of the proportion of small covering sets to larger covering sets. So that's another direction. When we haven't done any serious calculations, there's another direction in which one could look.
For instance, if you have a let's say stochastic process, and some fractal properties depends on the behavior of covariance function at 0, and another at infinity, like long range dependent. And basically, different theta simply show you all how object depends on the behavior of covariance function on infinity, and different theta show you how it behave fractal property about depends on the behavior of covariance function at 0.
Yes, certainly for other stochastic processes where the covariant structure is more complicated, I think intermediate dimensions might well give you more information.
Probably we could pose this question to the practitioners who are applying multifractal theory to turbulence. Next week we have like 2 talks, so maybe we could ask them.
Yeah. I'll be interested if I have anything useful to say. Yes.
Yes, why not? That would be very nice, very nice. Uh, 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 just as a commentary, and please correct me if I am wrong. So I assume this multifractal was first done by Fritsch and Parisi to applications of turbulence.
Yeah. And Halsey and so on were, I think, there was a group of them. Halsey, forgotten who the others are, but there was a paper by about 4 of them who really first introduced, physicists who first introduced this. Yeah.
There has been very limited attention so far, but I see there are like some people who have been who are working on it. So within the seminar series, we have 2 more talks, and there are some other people who are applying multifractal to other areas of applications as well. And furthermore, I'm very happy to see that you made the connection with fractal to stochastic processes, because from stochastic processes we can also go to fractional as well. So this completes this more or less completes the whole cycle of a cycle. Now you can also look turbulence as a stochastic process as well, but happy that you made a commentary about the link as well. And of course it's a massive undertaking, so we understand that part. So so you come from a mathematical perspective. We have someone who's gonna be talking about stochastic processes. Last year we had a couple of them who talked about stochastic processes, and we have some on applications as well.
Yeah, I mean, one of the applications of these stochastic processes is sort of in economics. If you look at if you look at share prices, you've actually got data available over very large ranges of scales. I mean, if you look at a graph of share prices over a year, and another one over say a minute, given that trading is essentially instantaneous nowadays, you wouldn't be able to tell which graph was which just by looking at them, because essentially you've got a self-similar or self-affine process that's being realized.
Yes, yes. I mean, fractional and stochastic process arising from this is finding applications. In fact, I recall a very recent talk. I think Edmund, his name was Edmund Zhao. Is Zhao. So he used this fractional PD and this this jump levy processes to design medical devices, and that medical device actually worked very beautifully. It will reduce the infection. And it was so successful that he was able to manage to get a patent as well.
Yeah.
So that was quite an impressive feat of achievement too.
Yeah.
Uh, so let's keep talking about it, and eventually, hopefully, before in our lifetime, we'll see more of these things.
Yeah.
Hopefully, my fingers are crossed. All right. Are there any more questions or comments?
Oh, okay.
All right, then I believe it's a good point to stop here. Thanks, Professor Faulkner, for the nice talk. It was very nice having you today.
Well, thank you for your hospitality, albeit virtual. I mean, I've never visited Trieste, but maybe I should someday. Anyway,
Yes,
nice talking to you all, and nice.
yes,
It's
yes.
an absolute pleasure to participate in your seminar.
It
Thank
was a
you very
pleasure for
much.
us as well.
Okay, right. I will